All right, guys. So we're going to go over the quiz number 8. Let me go ahead and share the screen. Okay, let me see if I can get. Okay, so hopefully y'all can see that.
Yes.
Okay. Okay, so number 1, which of the following is not a characteristic of an op-amp? Okay, the answer would be C, DC instability, because they do have a high open loop gain, because right here, open loop gain, it's infinity. So high input impedance right here is an input impedance. It's supposed to be high, and then the output should be very low. That's close to 0 ohm. So you have A, B, and D are correct, but C is not correct. So the answer is C for number 1. Okay, and number 2, when 2 equal signals apply to the input of balanced closed loop op-amp circuit, the output signal is, the answer would be B, as in Bob. For number 2, that is the basic op-amp. So anything, so that's like the differential amplifier. If you have to put 2 different signals, so when you put the same thing, it's called common. That is common mode rejection. So they're going to reject the whole thing, and it's going to go 0 output. So the answer is B as in Bob for number 2. Number 3, for the general purpose practical op-amp, an open loop voltage gain is about, okay, this is from the handout. The open loop gain is approximately about 200,000. So the answer is C as in cat for number 3. So any question on with number 1, 2, or 3?
No.
Okay, everyone's good. Okay, next set. Okay, so this one, okay, so number 4, in an open loop configuration, an op-amp are more sensitive to small inputs of voltage variation. So the answer is A as an apple for number 4. That is going to this basic op-amp. So remember, we only put in very tiny part. It could, if it's over the 75 microvolt, it can be taken into, it could go into saturation. So even a tiny part would affect that signal. So that's why it's more sensitive to small input signal variation. Okay, so number 5, in a DC circuit application, closed loop gain is directly related to the op-amp. Mainly the internal component, the external component, because it's, so the DC is affected by whatever the gain is, like the RF and RI. Okay, so that's external from the op-amp, which this is the op-amp right here. So everything on the external is the one that affecting the gain. Okay, so the answer is B as in Bob for number 5. Number 6, a quad op-amp is in single packet with, now this one, yeah, we haven't covered in class yet, but it's deal with, so you have is something like an you have a op-amp like this here. So it's packaged, so you got op-amp number 1, 2, 3, and 4. So the answer is D as in David for number 6. There's 4 op-amp in that one IC, okay? So quad mean 4, so it means there's 4 op-amp in the IC.
I thought 4 pin on each side.
No, the 4 pin is, that's good try, but that is only what you have, only that would consider the single packet.
Okay.
So this is a quad op-amp.
Thank you.
You're welcome. So any question number 4, 5, or 6? Okay, no question. Okay, number 7. Let me reduce this one just a little bit. Okay, so number 7, op-amp possesses, well, yeah, so you got 0 voltage, you have a 0 voltage gain, you do, okay, they do not have a 0 voltage gain, they do not have low input impedance, they're supposed to have high input impedance, They're not constantly constant bound. No, the only thing that apply is low output impedance. So the answer is B as in Bob for number 7. That goes back into this one right here, the output impedance and the input impedance and the open loop gain. Okay, so we want low output impedance. So B as in Bob as for number 7. Now, number 8, for DC application, the gain of the inverting amplifier circuit essentially equal to, this one is the RF over Rin. So the answer is B as in Bob for number 8. Okay, number 9, if the circuit load resistor is very within design limit, the circuit voltage gain. Okay, so now voltage gain only have to do with the feedback resistant and the input resistant. It does not have anything to do with load resistor, okay? So therefore it's gonna be, the gain would be stays the same. Okay, so we can increase the load here. It won't affect it's only affected by the gain here, the RF and Rn, but not by R5. Okay, so any question number 7, 8, or 9? Okay, next set. Okay, number 10, to increase the circuit gain. Okay, to increase the circuit gain. Now this is inverting amplifier. So it's going to be RF or Rin. Okay, so either now to increase the circuit gain, now we have to increase the RF or decrease the Rin. So therefore decrease Rin right here. We didn't increase, so this one's an increase Rin. No, that's incorrect. Decrease RF. No, that would be incorrect. So the answer is only B is correct for number 10. B as in Bob for number 10. Number 11, the inverting input of an op amp shown is, okay, so inverting input. So inverting input, so right here is your op amp. So what is going to your inverting would be at this point. This point is represent the virtual ground. So the answer is D as in David for number 11. Okay. Number 12, the circuit output voltage measure -2 volt. Based on the circuit values, what is the circuit input voltage? Okay. So we know that, okay, so we got this here. So we look at the gain of 10 right here. Okay. So gain of 10, so therefore this one is going to be 2 volts. So therefore, so we're going to take this divided by 10. So divided by 10, and since this is negative, so this one had to be positive out here. So therefore it's 0.2 here. Okay, so the answer is C as in cat for number 12. Or you can use the whole formula and calculate that out. Okay, so in equation number 10, 11, or 12.
Yeah, just a quick clarification. Understanding that Rn is going to influence most of the voltage input going into that circuit.
What do you call it? You're talking about 10,
for
11,
number 10. Number 10. Excuse me.
Okay.
RF is controlling a lot of that input, correct? It's causing the draw.
Yeah, that we can consider the gain. Yeah, the gain that would be.
So if Rn is causing a increase in the gain because the value of Rn is decreased to allow more flow of current or voltage, what's RF's controlling function of the voltage and current going into Rn that does not influence the increase or decrease of the circuit in itself? What is RF's main function as like is it more of a sensitive control variable?
Mainly it's set up just for the gain. It's for mainly the gain. If you decrease the Rn, that means your gain would increase. It would be your increase getting bigger and bigger. So your output would be much bigger. So if you put a 2 volt here and say that this one has a gain of 10, now this one becomes, so if you got a 2 volt, you're going to have a 20 volt out here. Now, if you decrease this one by a factor of 10, then now you have this one will become over. There will be a gain of 100. So 100 times 2 will be 200 volt output.
Okay, RF is not control any current.
Thank you.
Okay. All right. Any other question on 10, 11, or 12? Okay, everybody's good. Okay, next set. Okay, based on the given circuit information, the value of RF is, okay, so we got from 2 to, so 0.2 to -2. So a factor of, look like a factor of 10. So if this one is 5, so 10 times 5 would be 50. So 50K would be your RF. So the answer is A as an apple for number 13. Okay, number 14, for inverting amplifier to reproduce input signal with a wide range of frequency, the amplifier should possess, they should possess a wide bandwidth, because so that way you have more signal to look at. Okay. So the answer is B as in Bob, for number 14. Okay, number 15, the bandwidth of an inverting amplifier is measured at the, we measure mainly at the critical frequency. Another one for it is the cutoff frequency or breakpoint frequency. So, or same thing as the -3 dB. So the answer is A and B. So therefore the answer is C is the most correct. So C as in cat for number 15. So both of the above is correct. So any question, 13, 14, or 15? Okay, no question. We'll go next. Okay, let me see, scroll down just a bit. Okay, let me scroll a little bit more. Okay, number 16. Based on the circuit information, the correct circuit current is or we're ignoring the direction. So therefore, so we can calculate current. So therefore, your IL will always going to be 1 milliamps. IF is always going to be 1 milliamps. IN is also going to be 1 milliamp. So the answer is D as in David, all of the above for number 16. Okay. For number 17, if the positive voltage is applied to the input of a non-inverting op amp, the output voltage is, so we put in the positive here. So we're going to get positive output. Okay. So on the non-inverting, so we're going to get positive answer. So A as an apple for number 17. Number 18, a decrease in circuit bandwidth results from an increase in the value of, okay, so now, so if you have decrease in bandwidth, so therefore you have to increase in your gain. So how do we increase our gain? So in order to increase our gain, we have to increase R2. So therefore increasing the value in R2. So R2. So right here. So the answer is C as in cat for number 18. Okay, so if you need more information, this one was covered in lab volt. It's called the GBW, which is equal to gain time bandwidth. I see lab volt on transistor amplifier. So when you get to work on the transistor amplifier, you will understand more about this circuit right here. Okay. So that's it, number 16, 17, 18. Any question on those?
Yeah, just for 18 and R2, that kind of applied to my thought process as to R2's main function. 18 says that a decrease in circuit bandwidth results from an increase in the value R2. So if there's a decrease in circuit bandwidth by R2, we're making sure our center frequency, or the R2 center frequency is becoming more of a less noise and more direct and a clearer signal for
No, we're looking just we'll mainly look at the bandwidth. Either we look at the wide bandwidth or we go look at the narrow bandwidth. So if you look at, let me see if I can do this one here. So, okay, let me see wide.
Oh, it's technically making sure that our preferred frequency has
wide
a
band.
Yeah. Has a clearer signal, right? I mean, it makes it more clean, less.
No, wide bandwidth or narrow bandwidth. Okay, so let me see images. So you got something similar to this one right here. So you have something like with a lot more band. So you have much wider bandwidth, which is right here. Let me see if I can, here you can get it, that one to look at bigger. So something like this here. So if you decrease, let's see. So if you decreasing the bandwidth, so therefore you have to increase your gain. So this right. So it's something similar here. So it has not
doesn't have anything to clarifying the carrier and having it more sharper in the signal or cleaner signal or clearer signal.
No.
Or frequency or channel, excuse me.
No.
Yeah, nothing. Yeah, look like nothing had to do with channel.
All right. So, all right, it's misinterpretation. All right, thank you.
Yeah. So when you get to work on the level, you go to work on the transistor amplifier. It's called the GBW or gain bandwidth, and I'll explain a lot more clear on it.
Now the thing is, at the beginning, we're already telling you what the bandwidth for open loop gate. What the frequency?
F1 minus F2 or
Yeah, but the thing is, at the beginning, we already telling you what frequency for open loop gain. That means the gain is 200,000. If you're looking on that, you can tell me what the bandwidth.
Open loop gain.
In the op amp. And out. Okay.
for number 3?
No, it's just referring to the basic op amp. Basic op amp. Let me see, op amp.
Well, what's the expected gain as far as from input and output?
Going down.
Okay, so
keep going down. Just going down until we can see it. Right here. That is the one. When you're looking into the picture, how many students understand? Okay, you can see. That's what they're using open loop gain 100. Okay. And this is the bandwidth. And the bandwidth only 10 hertz. Okay. Right here. That only 10 hertz. We cannot using bandwidth only 10 hertz. You want that a more frequency. In order to get a more frequency, you have to reduce the gain. You see that? This is the gain to 100,000. That 80,000, the gain go up to 100 hertz. And they keep reduce the gain. Okay? So you want more bandwidth, then you have to reduce the gain. That's only the question. Nothing to do with the sub or noise or whatever. Who cares? So that's why when you guys see this picture, try to understand Okay, for the big open loop gain, you get bandwidth on the 10 hertz. Now you want 1 kilohertz, 10 kilohertz or more. That means the bandwidth must be reduced.
The gain had to be reduced here and you get more frequency. You reduce it more here, you get more frequency.
Exactly.
Or less ripple, right?
Yeah, we don't care about ripple.
But the lower your gain, I mean, when you're trying to get lower, you're trying to actually get a lower ripple, right? You want as straight as line as possible.
Yeah, that's different story. But the question they just asking for, if you want more bandwidth, what can we do? That telling you you need to reduce the gain, increase the gain. And on number 18, okay, they increase the value, okay?
So they want increase here?
Yeah.
Yes. So you want to decrease the bandwidth. So decreasing the bandwidth, you have to increase the gain. So how do we increase the gain? Now the gain has to deal with R2 and R1. Either we decrease R1 or increase R2. In this case, they tell you to increase. So the only thing that you can increase is your R2.
Or you can reduce.
Yeah, you can reduce, but this question, they tell you to only to increase the value. So the only thing you're allowed to increase that would make the circuit true is the increase R2. Okay. That's from this day. Okay, you're welcome. Okay, so back to you, Mr. Pham. Thank you.
Thank you, Sam.
You're welcome.
Okay, today last day for 2021. And
hey, last day.
for lecture, the lab still get Tuesday and Wednesday. Okay, and the last day will be out Wednesday. Then you get a holiday. Return on January 3rd, 2022. Okay, so any question regarding the schedule for this holiday?
Yeah, I just looked at the website and it hadn't been modified, so I guess that'd be the only question. It's still last week's schedule.
Oh, okay. Sorry. The thing is only 3 days, so that's why I'm not put on. I already let your guy know.
I also got confused by that too.
I was expected to go to school tomorrow.
Okay, so that's why you have to be in the class.
And no potluck, right?
Yeah, no, well,
Yeah, we're gonna have a potluck. Yeah.
no, we'll have no problem in class on the time. Okay, so
Hello, everybody.
before we start with the lecture, okay, the last one I will be talking about last week already something for JFET transistor. But another thing I can tell you before the end, if you're able to understand what we're talking about in the program, basically all of the stuff like DC, you know, transistor amplify, filter, JFET, everything. That will be help you to do your job as a technician. And also, after this program, you really understand, you can go to the college. Okay, will be no problem. I get a few students. They were completed program year ago. And at this time, they had the UCSD with the double E major, electrical engineering. And they will be graduate on December 2022. One more year. And they told me this program help a lot. They don't have any problem to study at the UCSD. What I try to do, I try to let them know I want what they talking about this major at the university. Okay, I try to collect and try to help any student after the program you want to be going up to be engineering. Okay, the thing in my school quite different. University of Florida over 40 years ago. Now it's not really up to date. So I want to know what at the UCSD, what they're talking about. Okay? Then whoever want to keep going, I can share to you. Okay? So, when I said you understand, that means when you see the quiz, you understand right away which one is correct. I'm not giving much calculation in the quiz. That just requires understanding. Calculation, very simple thing. You have to do it. Okay? So, if you not quite understand the lecture, just let me know. We'll find out the way can help you. However, make sure now or future for your career, have you reading textbook or the handout over and over. For this program, I not expect you to reading any textbook, but at least my handout. Okay, you have to understand and can answer the question quickly. Okay, now I share my iPad. Okay, this time we're talking about DC bias. Either transistor, NPN, PNP, bipolar transistor, or JFET, they need the power to make it work. Okay, so that's why you get the first part will be a DC bias for JFET. And after that will be amplifier. So I hope I can get it done. First week, of the spring cementer. Okay, so now I go over. I said any question, anything you still not quite understand, go ahead and let me know. Okay, the JFET, that got a field effect transistor. Okay, and basically they working a reverse bias. Okay, now if you're looking into the picture, okay, you get this one. You have to recognize right away N channel JFET. And the JFET, they get the gate, the drain, and the source. Okay? And this one will be a P channel. Same thing. Only thing the difference will be one arrow coming in, one arrow coming out. The same thing like you looking into the bipolar transistor. You're able to recognize is it an NPN or PNP. Okay? And also, they will be telling you these are physically, okay? That for N channel and that for P channel. Basically, electron will be moving from the drain to the source. Electron moving, that's why you can get the current, okay? And that they call a channel. Okay, now let's see. This is the explanation. Okay, VDD, that's a VDD. Provide a drain to source voltage and a supply current from the drain to the source. VGG, that's right here. Set the reverse bias voltage between a gate and the source. JFET always operate with the gate source PN junction reverse bias. PN to be forward bias, not reverse bias. And this picture just telling you, this is a channel from the drain to the source. Okay? This channel wider, more current flow. Okay? If a narrow, less current. So they just given to you the picture here. You see that VGS, that will be more negative. Then the current, you get a leader here. Okay? And now on this picture, they reduce negative voltage and the channel wider, more current flow. So that's why when they measure the current, you can see AID will be increased. That's the only thing you need. And also they given to you the picture for the JFET, whoever working in left wall, you have to deal with this guy, okay? Same thing, okay? Wider channel, then more current flow. To wider the channel, you have to reduce the negative voltage, okay, at the VGG. So if you question, then let me know. And now, if you're looking on the display here, this stands for ID, current ID. And this stands for VDS, voltage from the drain to the source. Okay, so this is the code for the current. Now, first thing is, this is the current ID keep changing up to a certain point at what they call a VP. VP stands for pin off voltage. Okay, at start from a VP, the current ID now will be constant and equal to ID at F up to point C. Okay, and that will be a breakdown area. We don't care that one. So from 0 up to VP, pin off voltage, JFET will be in ohmic area. Ohmic area, that means JFET can be using at a resistor. And from VP up to the breakdown here, they will be a constant current area. In order to get the wider channel, they're asking for VGS equal 0. So the question is, what is IDSS? What is it?
It's the max current.
I understand the maximum current, but still need more information. IDSS, that is the maximum current of the JFET. I still need a little more. Who tell me?
The saturated current.
That also another name for constant, okay.
The gate shorted.
Okay, just a minute. Constant current area, same thing they say saturation, okay? But I still need more and more for that definition for IDSS.
Is it the maximum current when the gate and the source, I mean the drain and the source is shorted?
Exactly.
Or
That's
when
what
or gate?
IDSS is the maximum current when VGS equal 0. VGS equal 0, that means the gate and the source will be shorted. That is a basic definition, okay? And IDSS will be given by manufacturer for each JFET. You cannot do anything. However, you must understand the definition for IDSS. Maximum current with the VGS equal 0. Or you can say the voltage from the gate to the source shorted. Same thing. That is that you really understand it. So that's a very simple thing, okay? Any question? Okay, if it's not, this is your guy need to read over. The maximum drain current out of the JFET occurs when gate source voltage is 0. Or you can say VGS shorted. That's the same thing. The drain current is almost constant in the region between VP and VDS max, okay, before they break down. If the drain voltage is too large, the effect will be breakdown. JFET act like current source when it is operating along the almost horizontal path of the drain curve. That means the constant between VP and the VDS maximum. The minimum voltage of VP equal a pin off voltage. That's what you need to memorize. Or when we're talking about VP, you don't know what that means. Okay? The maximum voltage VDS max equal a breakdown voltage. That means they be breakdown. Between pin off and breakdown, the effect acts like current source with the value of IDSS. IDSS stands for the current from the drain to source with shorted gate or VGS equal 0. That's what I'm asking you guys. Basically, based on the handout I gave it. So that's why I said, you want to understand, you have to read over and over. Okay? Between pin up and breakdown, they effect act like current source with the value of IDSS. Okay? And also they've given you the definition for the IDSS. And then you get the ohmic region. The almost vertical part of the drain curve equal an ohmic region. That equivalent to the saturation of the bipolar transistor.
Mr. Pham, question?
Yeah.
This might be slightly wrong, but when I'm interpreting the current, is it very similar in the pressure effect of the chemical exchange or the chemical stability of a electrolytic capacitor?
No.
Before?
Okay, just talking about basically JFET, not try to see how they do affecting into something else. Don't try to confuse that. When they design JFET, they have to deal with whatever they need. But right now, we learning basically how the JFET working. So you better go to university. Then you can learn more when they using JFET to design something.
Yeah, it just sounds like there's a storage effect that's occurring before work either stops or starts. So it has a resemblance to the pressure effect of inside of a capacitor. All right, excuse me, I'm just thinking.
Okay, no big deal. Okay, cutoff voltage. The value of VGS that make ID drain current approximate 0 is cutoff voltage. That means cutoff voltage at the point ID equal 0, no current. They call it VGS off. The JFET must be operate between VGS equal 0 and VGS off. Okay, what is the VGS off? VGS off, that means at the point current ID equal 0. Okay? Comparison, opening up and cut off. VP is the value of VDS at which the drain current becomes constant and it always measures at VGS equal 0. VGS up and VP are always equal in magnitude but opposite in size. That means VP positive, VGS up will be negative, and the value will be the same. Okay? Data set usually will give an either VGS up or VP, but not both. If they given you VGS equal minus 8 volt, then VP must be plus 8 volt. They just off the side. Okay? That's just a definition, nothing else. And you have to follow it. Okay? Don't ask me why. Now, you can see the picture. It's a family of the drain characteristic curve. So, this stands for ID. This stands for VDS. The curve here stands for VGS. That I try to understand. Same thing in the bipolar transistor. This will be IC, okay? And this will be VCA. And the curve will be the IB, okay? However, in the JFET, this stands for ID. This stands for VDS, and the curve here stands for VGS. For example, VGS equal minus 4, minus 3, minus 2, or minus 1. Up to the point VGS equal 0, you're looking for ID. Then you see ID equal ID at S. Okay? And they telling you the pin off, okay? Right at this point here, VP equal plus 5 volt, okay? And at this point here, pin off will be equal 1 volt, or VGS equal, let's see, that's the VGS, okay, equal minus 1 volt. Okay, they given the note, very important. JFET is a voltage controller device. How come they say JFET is a voltage controller? Who's telling me? That's a very, very important to you guys. How come?
Is it because what you got at the top where it says VGS controls ID?
Exactly. VGS control ID. You can see right here. VGS equal minus 4. And the current here will be ID. Okay? And if they using minus 3 volt, and this current ID here. So basically the current ID depend on VGS. So that's why they said JFET is a voltage controller device.
And Mr. Pham, I have a question.
Yeah.
My question is, maybe you already said it, maybe I missed it, but where you have like VP equal plus 5 volts in blue, and then in the pinch off when VGS equal minus 1 volt, the pinch off and the VGS when VGS is negative, are they like one and the same? Because the magnitude of say the pinch off can be 5, but VGS can be -5 or something.
Okay. VP 5 volt, VGS equal -5. Okay.
Okay. All right.
This one is different from this one. Okay. But they talking about VGS. VGS equal -1. You couldn't see VGS in here, right? That's for VGS. Okay. However, when you next one, you can see VGS. However, VP at this point will be 1 volt, right? They the same magnitude, but they opposite in the polarity.
Well, like at the end of the graph, it says VGS equals VGS off, which is equal to -5. So that magnitude is different from the pinch off, which is +5.
Right. That they're talking about VP, not VGS.
Okay.
VP all the time, positive. And VGS will be negative.
Okay. VGS or VGS off?
VGS off.
Okay, thank you.
Or VGS in general.
Okay.
The last one will be VGS off. The thing that they said JFET working from 0 to VGS off. When we see more pictures, you can see. Okay. Now, JFET cut off voltage. At cut off voltage, ID equals 0. You can see right now in here, no more channel. Okay. So that's why no more current flowing from the drain to the source. Okay. And at this time, VGS now will be equal VGS off. Okay. Go back to the definition for VGS off. VGS off, that means VGS at ID equal 0. No ID current. Okay. Basic operation of a P channel is the same as an N channel device, except P channel requires negative voltage. You see that? This is a P channel. Then they need a negative voltage, VDD. N channel need positive voltage. That's what you need to know. Okay, example. For the JFET circuit show, they given VGS off equal -4 volt and IDSS equal 12 milliamp. They say determine the minimum value of VDD required to put the device in the constant current of operation. Okay, now you can see the solution. VGS off they given to you -4 volt. Then VP must be 4 volt. Okay. the minimum value of VDF for JFET to be in its constant current area. That means VDF must be equal VP and equal 4 volt. Okay, in constant current area with VGF equal 0, ID equal ID at 12 milliamp. The drop across the drain resistor RD, VRD, ID times RD, you get 6.72 volt. Apply Kirchhoff law around the drain circuitry. So VDD equal VDS plus VRD. 4 volt plus 6.72 volt. And you get 10.7 volt. Okay. They want to determine the minimum value of VDD. Okay, so VDD from here, there you go. You get a voltage drop across RD, and you need the voltage for the VP also. That's why 4 volt for VP. And now you have to calculate how much resistance, voltage across RD. Then you add them up. Okay, JFET transfer characteristic curve for N channel. ID equal 0, 0 right here. At this point, ID 0. So you get a VGS off point right here. ID equal IDSS. That means this is ID. This is the IDSS. And at this point here, VGS equal 0. That's basically when you're reading here, try to understand. The thing is, you know, at the time I was at the school, I couldn't understand. Basically, this is really news for the student later. At my time, maybe not. So that's why when they're talking about JFET, I not understand, but the thing is I have to teach. So that's why I have to learn. I have to study. I try to understand in order to able to explain for you guys. Okay, example. When VGS, okay, this is the curve, okay, for the current ID. ID be calculated by the formula here. ID equal IDSS times 1 minus VGS divided to VGS of square. Okay, so this equation stands for that curve right here. That's a little complicated. Okay, now at this point here, IDSS equal 12. At this point here, VGS of equal minus 5 volt. Okay, so at the curve here, if you want ID given you example, this one here. Then you can go to the ID. You know that will be 8 milliamp. If you want to get the VGS, you going down. And the VGS equal minus 1 volt. They just given you few point. Okay? What current ID and what the VGS equal. That one will be VGS off. So that's why they say JFET working from VGS equal 0 here up to VGS off. And this is any value of VGS. Okay. On the right side here, they just display the current, the voltage VGS. You see that? With VGS equal minus 2 volts, then you can get this point, and so on. Okay, let's see. Example. Function data sheet for JFET indicate that typical IDSS equal 9 milliamp. VGS off equal minus 8 volt. Using this value, determine the drain current ID for. First thing, VGS equal 0. So what the current ID equal? VGS equal minus 1 volt, and so forth. Okay? Number A, VGS equal 0. Then the current ID equal IDSS, 9 milliamp. Okay? You don't have to do any calculation. Now, if VGS equal 1 volt, supposed to be minus 1 volt. Okay? We see VGS equal minus 1 volt using the equation I just telling you. ID equal IDSS times 1 minus VGS over VGS of square. So IDSS is 9 milliamp. VGS equal minus 1 volt. That's what they want you to do calculation. VGS of minus 8 volt. And you come up with the answer will be 6.89 milliamp. And if they want minus 4 volt, you can using the same formula to calculate, and the answer will be 2.25 milliamp. Any question about this example? Normally, in the test of the quiz, if I asking for calculation here, I can give you the formula. You don't have to memorize the formula. Okay? If you can do it, that's much better. However, if you see the formula, you're able to do the calculation. Okay? Okay. JFET forward trans conductance. The forward trans conductance, that means the transfer conductance. GM is the change in the drain current for the given change in the VGS. The definition for GM is that delta ID divide delta VGS. the unit of the GM is Siemens. Data sheet normally given the value of GM at the VGS equals 0 is what we call GM0. When you read it, make sure something emphasize on that and you try to memorize. They can ask you, what is GM0? Okay? The definition means GM0, that means the forward trend conductor at VGS equals 0. Okay? And normally given by the manufacturer. The GM can be calculated at the following. You want to calculate the GM, you can using the formula GM0 times 1 minus VGS over VGS up. Okay? Or GM0 you can calculate by the formula 2 times IDSS divide the absolute value VGS up. That means they don't want negative. GM0 just a number. That's why you not try to divide by negative. They want absolute value. Okay? So for the forward trend conductor, what I recommend you just memorize the basic definition. That means the delta, the ratio between the delta of the ID with the delta for VGS. On the picture, they already show you. But this, we don't care. However, you need to know how to calculate the GM. Okay? You need to know GM0. Okay? And GM0 normally manufacturer given to you. If not, then you can calculate by formula 2 times IDSS divide to VGS off with the absolute value. That only just make sure you try to read over, try to understand. Okay? If you can memorize the formula, this is the best. Let's see, example. The following information is included on the data sheet, okay, for the JFET UN5457. Typical IDSS 3 milliamp, VGS off -6 volt, and GYM0 5,000 microsiemens. Using this value, they want calculate the forward trend conductance GM. Okay, for VGS equal -4 volt. The value of ID at this point. Okay, so you can see the solution. Okay, you using this formula. And the answer will be 1667 microsiemens. And the current ID will be 333 microamp. Okay? Okay, any question? Otherwise, you're gonna have to exercise. Okay? And another example, they want to calculate the input resistance. Okay, and Rin equal absolute value, okay, of VGS and IGSS. They already gave it to you here. IGSS equal minus 2 nanoampere and VGS equal minus 20 volt. Just substitute to the equation. Okay, they want absolute value. And you get 10,000 mega ohm. Okay, we already talking about JFET. Voltage controller device. Okay, my question is, what on the bipolar transistor? They what? Voltage controller or current controller?
Current controller.
Current, right?
Right.
Current controller. The thing is you already know, in a bipolar IC equal beta times IB. If you change IB, then you change the current IC. So basically depend on the current. Okay? So bipolar is a current controller device. However, on the JFET, you're changing VGS. You're changing the current ID. That's why for the JFET, it's a current controller. Okay? Now we're talking about JFET bias. DC bias. You understand either bipolar or JFET, they need the power supply to work. Okay? Many techniques can be used to bias JFET. In our case, the gate source junction is reverse bias. The most common bias technique you can get a gate or fixed bias, cell bias, and voltage divider bias. And the last one, current source bias. Okay? That means in order for the bias working, we need the power. So they can using the fixed bias or they go again. Cell bias, voltage divider bias, or current source. Okay, now see what happened here.
Mr. Fan, question.
Yeah.
In the biasing, can a ground, or let me ask it differently. What different types of grounds are there? Copper and gold, silver, right? So would a ground plane made of a certain material
No.
cause a certain bias?
Not depending on N channel, P channel. But we're not talking about building. We just try to see how the first one, that means the fixed bias, how they working, how do your calculation. That only very narrow in that area.
Thank you.
You're welcome. Now, first thing we're talking about fixed bias or gate bias. Okay, so basically, you understand it, they draw, including AC. However, AC is not affected to the DC. Why? The thing they did, capacitor, same thing in the bipolar. DC blocking AC coupling. However, they put in here, they try to explain a little more thing. Now, okay, when you see this circuitry, and you must be recognized, this is a fixed bias or gate bias. The thing is, at the gate, you can get a negative voltage, minus VGG. Okay? I given you example. Okay? RG equal 1 mega ohm. That means very big resistance. So if you get a minus 2 volt in here at the gate, what the voltage here?
0.
If I get an example, okay, I say you get minus 2 volt. So VGS, we get, right? Equal
0.
how much voltage?
Is it 0?
1. Who else? Okay, look like nobody. I can,
Rephrase the question again.
the question is, if I said I get VGS equal minus 2 volt, so question is what VG? That means the gate voltage equal. One student say 0. Who else? I'm not saying right or wrong. So that's why I need more input. Who can tell me?
Well, there's no AC signal.
No, we don't care about AC.
Well, that means, I mean, you can't block any DC, so DC has to go all the way to RG, correct? So technically, VDD is flowing to VG.
Very simple thing.
The 2 volts, positive 2 volts.
I said you get here minus 2 volt. My question is, V at the gate equal how many volts? Okay, now I can tell you. The resistance RG very big. My question is, the current flowing here equal what? What current?
2 microamps.
Equal 0. Too big resistance, current cannot flow it, correct? Then the current have to be 0. And if the current equals 0, that will be telling you the voltage at this point and the voltage at this point will be the same. So they will be equal minus 2. If you not agree with me, just go ahead.
Mr. Pham,
Yeah.
The only problem made it hard to understand this. We didn't know what the value of RG is.
Now that's what I already telling you. Very big.
Well, what do you consider to be very big?
1 mega ohm up.
Okay.
That's what they given you on the other picture, 1 mega ohm. Only thing that they just telling you, current cannot flow through it.
I mean, now that you say it's 1 mega ohm, it makes sense because resistance is the opposition to current flow. And if it's a really, really huge resistance, then current won't be able to flow.
Right.
Only thing I was saying, it would have been nice to know that RG is like 1 meg or bigger.
That's what I said. They already given to you right here. 1 mega ohm. And you know why they equal V get equal minus 2?
Can you tell us?
That's why I want the guy really understanding. Now, I telling you, if I flow in here equal 0, that means no voltage drop here. So the voltage at this point and this point will be the same. The thing that they not drop any voltage. That's it.
So the resistor, we can treat that like a regular straight piece of wire then, correct?
Now, they just like resistor, not a wire. Wire will be less resistor.
Yeah, well, that's, okay, all right, okay.
If RG were emitted, so it's technically no resistor. So technically it's still -2 volts. Because if RG were emitted, it's -2 volts.
That
Like you said, there's no component.
we get, basically you don't need RG, right?
In this situation, no.
Okay, that's what step by step. Make sure you guys understand why VG equal -2 volts. Okay, now you can connect directly to the gate without resistor. It's still -2 volts anyway. But you cannot do it. I'm telling you why. Now, basically you're using JFET for the amplifier. What amplifier try to do? Try to increase your signal, your voice, right here. Okay? So now, if you connect directly to the gate without RG, when you go into the AC module, for the AC module, then basically you can get a sideways go in here. And the VGG must be connected to the ground. We already know from bipolar transistor. DC voltage will be routed for AC. So if you route it here and the sideways coming in, they will short to the ground. They cannot go to the JFET. That's why they need that resistor. If you get the resistor here, that means you still get the sideways here. They not be short to the ground. That's why they need RG. You can see they draw here. Without RG, they short the gate to the ground. The thing is, my not VGG DC voltage must be route. So signal sideway will be go to the route, not go to the gate. They can go to the gate. The thing is you get a resistance here. Okay, isolate from the gate to the route. Okay, any question?
Just one last thing, Mr. Pham. So on that, are you saying that for AC that resistor, well, it'll be short to ground if
right down here. They say AC route. You understand for the bipolar same thing. On up the DC power supply, when you're working for the AC power, DC power supply must be routed. And without RG, then the gate will be short to the route. And the sideway coming in, they go to the route, not go to the gate.
And you don't want that.
No, for sure. You don't want that. You want to amplify your voice sideway. So that's why I try to explanation for instead you connect VGG directly to the gate, but you cannot. The thing is, AC signal cannot go to the gate anyway.
Mr. Pham.
Yeah.
So -2 volts is DC?
Yeah. Yep.
Right, so VGG is a negative supply, and VDD is a positive supply.
Right. They must be routed.
So if -2 volts is being used to open the gate, would that change that circuit to 18 volts?
No.
At what point is that 20 volts going to flow to ground with the -2 volts at gate? Does that -2 volts have to be converted to +2 volts to open up that
That's
gate?
not around. That's not reality, right? When you're working, you cannot sort it to route. But in order solving for any AC problem, you follow the rules. They're already telling you. Capacitor must be sorted. You cannot see any capacitor. DC power supply, no matter positive, negative, they must be short to route. But that is not, really reality. The thing is you cannot do it. Okay. If you sort the VDD or VGG to route, but the JFET not working. However, we're talking about solving the problem for AC signal.
So if we wanted this circuit to technically work, we'd put a load there between the gate and RD.
You mean the resistor?
No, RD. Above the gate, RD resistor, right? So between gate and RD, we can put a load there, and technically the circuit would work. In the sense that the voltage is going to show a current flow.
No, basically you get a current flow here, right?
Right.
However, what I'm saying is, you want to solving for AC circuitry. This supposed to be route. That not happen in reality, right? If you sort it to route, they're not working at all. But what I said, for solving the AC problem, you must be doing. You cannot do it anyway. don't talking about reality. Okay? They just talking about you want to calculate the gain for the amplifier. You must be follow the rules. When we're talking about AC, then on DC must be shorted. Okay, so basically now try to explain to you why we need RG. Okay. Okay, now this is just try to introduce, okay, how gate or fixed bias circuitry look like. That's what I already showed you here. Okay, when you see this circuitry, you must know this is a fixed bias or gate bias. And then when you see another circuitry, this is a circuitry here. And they call a cell bias. Okay? One of the most common ways to bias the FET cell bias. Only a single power supply yield the drain supply voltage. Okay, VDD. If you're looking on this circuitry, and you can see you don't have a VGG. Okay. However, to solving the AC, they need the graphic. Okay. This is a graphic here. They have to give it to you this graphic so you're able to do. Okay, now we go into this circuitry. VGS equal 0. Why? Why they put in here VGS equal 0? Tell me.
It's connected to wrong through the resistor.
Why they say VGS equal 0?
RG is equal to 1 mega ohm. So therefore, since it's grounded on that end, it's approximate to 0 then.
Yeah, it's the same as the other one you just showed us.
Perfect. This is around.
Right.
0. So that's why they put a VG equal 0.
And RG is so big that there would be no current flow.
Right. Let's try to explanation for why they put VG equal 0.
That's the same as the one you just explained to us on the other page.
Right. The thing is round here, 0. That's why VG equal 0. Okay, so next time when you're looking into the circuitry, you have to know what type of the bias. They can be fixed bias or they can be cell bias. Okay, on this one, they need only one power supply, that VDD. Okay. I'm not talking about any calculation yet. I'm talking about recognize bias. So when we go through it, you get a question and go ahead and let me know. I try to make clear, really clear for your guy. So that can save your guy reading more information. Now, next, bias. Voltage divider bias. So make sure you understand this is a VG and this will be VS here. So V from gate to the source, they call a VGS, okay? Gate source voltage. That's basically a definition. Now, basically, they're using the voltage divider, the same in bipolar transistor. You want to get a V gate, you can take a VDD times R2 divide R1 plus R2. And from the gate to the source, you can get VGS. Okay, now see, since the gate source junction has extremely high resistance, the R1 and R2 voltage divider is practically unloaded. Okay, so basically they can using two resistors instead using the power supply. Okay, the thing is resistor 5 cents for each. Power supply will cost more.
Hey, Mr. Pam, real quick question.
Yeah.
So VGS is equal to VG minus VS. Is that correct?
That basic definition.
Yeah, okay.
VAB means VA minus VB.
VGS equals VG minus VS.
VS.
Okay. I know, because I know this is a JFET we're dealing with, but in the case of like the bipolar, we were dealing with VBE for the base.
VBE.
Yeah, exactly. Whereas here we're doing with VGS, and we use VG minus VS to get it.
Same thing.
Right. Okay. Thank you.
Welcome. Now, voltage divider bias is more stable than either gate or cell bias. And also, they said you need the graphic to solving the problem, to do any calculation. Okay? So only 3 bias really need. And the next one, we don't need that. Okay? Basically, they call, let's see, this what they call current bias. Okay? Let's see. This example for what?
It says gate or fixed bias.
Okay, this is an example. They want to know for this circuit. Okay? They want to know VGSQ, IDQ. Now, I try to explain to you. VGS is VGS. When they say VGSQ, what that means?
They're referring to like some point on a graph or something?
That's the Q point.
Yeah, right, the Q point on the graph, right?
Right. That means the point on the VGS, okay? VGS in general. However, VGSQ, that means a certain point on the display.
That's where VGSQ and IDQ cross.
Right. They want to calculate the VGSQ at a certain point, IDQ at a certain point. And general, you get calculate the VDS, VS, VD. Okay, they given to you IDSS equal 5 milliamp and VGS off equal minus 4 volt. They want A VGS Q, B IDQ, CVS, and DVD. And I already given the solution to you. The reason I have to go through it today, the thing is, on holiday, you get more time to read, okay? When we get back again, I ask you questions, you're able to answer me. To calculate the VGS, VGS equal VG minus VS. VG equal minus 2 volt. I already explained to you. You get 2 volt minus 2 volt here. And V get equal minus 2. And VS rounded, so 0. So minus 2 minus 0, you get minus 2 volt. Make sure I go through 8 questions. You not follow it, let me know. Okay, make it clear. That is the first one to calculate the VGS. Second one, they want to calculate the ID. You're using the formula. IDSS times 1 minus VGS divide VGS off square. Okay? So, substitute the value. You can get ID equal 1.25 milliamp. You have to do your calculation. Make sure you get the right answer. And then they want to calculate the VD. VD equal VDD minus the voltage drop across RD. You can see the same in the bipolar, nothing else.
So you take VDD and subtract IDRD from it, and that'll give you VD.
Right. That means the voltage here.
Right.
So you should get the 9.25 volt. And also they make sure you understand that the current flow in here will be ID. The current flow here will be IS. However, if you're working with the JFET, make sure you understand all the time ID, IS will be the same.
Mm-hmm.
The thing is, when I try to prepare for this handout, only thing whatever you need to know. So I try to put in here and you try to reading over and over. Okay?
Mr. Pam, question on that.
Yeah.
I just got a real quick question. We deal with bipolar transistors, which is PNP, NPN, and JFET.
Mm-hmm.
But when it comes to the bipolar, you have IE and IC. They're almost approximately the same, and then with the JFET, ID and IS is almost the same. So I mean, is it you don't have like a beta or nothing for the for the FET?
Yeah. On the bipolar, basically depend on a beta.
Beta.
So they can tell you if they supposed to be IC, IE the same, but normally they not.
Mm-hmm.
They get a different.
And the JFET don't have a beta to worry about.
JFET, ID, or IS only one coder. That's what they're telling you.
All right.
Okay, and cell bias, you see, right now I'm not go through it, okay?
All right.
You can read. You see the circuitry, you know this is a cell bias. You don't need the power at the gate, okay? And in order to solving, you know, anything, you need the graphic here. They given you this curve right here, and you have to know how to get the Q point. That means the Q point at the curve telling you ID and VGS, okay? So that's why will be, you can try to read, but I agree well with you, okay? This is just to let you know how do we calculation, but practically, they don't want, the thing is take a lot of time, okay? Try to get the graphic.
But the self-bias, are you saying the graphing is the only way to solve that one?
One way, only one way.
Which is the graph?
Right, without you cannot. Okay? So, in order to solving the problem, then instead using the graph here, they can tell you, okay, I given you VD. Okay? If you get a VD already given to you, you can calculate the ID. Right? ID will be the difference between a VDD. Okay? You calculate the VD here, okay? They given to you. So you can calculate the current ID equal VDD minus VD divide RD. Okay, you don't have to apply the equation. Otherwise, you must be need the graphic. That's it. Okay, next one, voltage divider. First thing for voltage divider, you also need graphic. However, basically you can see, you easy to calculate the voltage here, right? Voltage divider. VDD times R2 divide R1 plus R2. Okay? So that's what we call a VG. After you get the VG, you can calculate the VGS. Okay? That will be equal VG minus ID times RS. Okay? VGS, that means the voltage here. Okay? Will be equal VG minus the voltage drop across RS. That's what you can get. VGS equal, they do calculation here. Okay. And then, now, you need to calculate the 2-point AB. Okay. I show you here. They given you the curve, the graphic here. If you want to know Q, then basically you have to draw the line, the cut, intercept the curve at the Q point here. At this Q point, you go this way, you know ID equal. You going down, you know VGS equal. The purpose is try to calculate the ID and calculate the VGS for either cell bias or voltage divider bias. Okay? And next meeting, I will telling you how can we get the point A and how can we get the point B in order to draw the line when they intercept with the curve That's what the one we call Q point. This example. Okay, and this for sell buyer. And I get another question is, the JFET is the on device or off device? Who knows? Tell me.
It's on.
Okay, you say on device. Why you say on device? What do you
50-50.
you want to understand what that means on device?
That it's mostly when the circuit gets turned on, it stays on.
No. I telling you bipolar transistor on device.
Well, then it's got to be off because it's opposite.
But
It's
this is an off device. However, I need a little more, proof. You know that why they call it off device. Okay.
Because you don't have that like you have VBE on the bipolar, you got VGS on the FET, but it works differently.
Now, on the bipolar, they call it on device. The thing is they will be controlled by the VB, right? If you don't have a power supply applied to the base,
Okay.
not working. Correct?
Okay.
However, for the JFET, if you're looking on this circuitry here, gate don't need any power. See, they routed here. However, they're still working. That's what they call an off device. Don't need that power.
Does it need that resistor in order for the gate to stay closed?
They must be that resistor. I already explained to you. Without this resistor, the sideway cannot go to the gate.
JFET off.
If you short directly to the route, then sideway will be short to the route, not go to the gate. Okay, then this is an example. Okay, if you are able to get the time to go over, okay, and next meeting, we get together. That's easy for you to understand. That is not a problem. Okay, and after we know how to calculate the DC bias, then we will go into the amplifier. Also, they get 3 configurations: common source, common gate, common drain. Same thing exactly in bipolar, CE amplified, CB amplified, CC amplified. Okay? Okay, now, any more questions?
Yes, Mr. Pham, before you started recording, did you by chance record today's document reference. So if I was to go look at the recording, I could see what documents that you wanted for today's lesson. Or is it possible that you can go back to your main page and reference the documents we need to be downloaded? Could you do that, please?
I think it was JFET Lowell.
But that the main share had like several messages on it. Is there any way we can review that before you shut down tonight?
Okay, I don't have anything on the reference.
No, the main page that you usually show for class. That
Okay.
usually shows the document to be downloaded and what your plans for the night is.
Oh, okay. For sure.
Please.
Will be put it into the handout. Okay. You can go to that handout and download. Next part will be what amplifier, JFET amplifier. And
Is there any way you could show that main page, your main share page, the lesson plan for the day? The first page you start off with class every day, every time.
you mean summarize?
Yeah, the summary or the lesson plan for. Would you show that, please?
No, basically for today, right?
No, you usually have the lesson plan displayed before you start your class.
Okay. I see what you say. Okay.
Yeah, it should be the first page.
I know. That means what we cover for the lecture today.
Yeah.
Okay. The thing is, on that one, they already recorded. However, next meeting.
No, that's what I mean. It isn't your PDF or your PowerPoint. It's the first page you always show as part of today's lesson.
Okay.
It lists.
I know. But the thing is, on recorded right now, we cannot do anything.
No, that's what I'm asking you. So if I go to the recording, will that page be displayed? And if it isn't displayed, can you reference it now to make sure that we have that page for reference as download and all your summary for tonight's lesson?
Okay, I can make it indeed modify for this handout, but I cannot do anything on whatever we recorded today.
You can't show the main.
No, I cannot. I cannot
Lesson.
control that.
You can't show the main summary or lesson for today? You can't show that page?
That's it for now. I understand. That's very good point. Summarize what we will be learning.
Well, it's just usually that first page you have popped up on the web.
I think what he meant is the page that you usually show before the class start.
Yeah.
Okay. Yeah.
Before the class start, you show like next week. I mean, for this week, we only
has the whole schedule of kind of what we're doing for the whole week.
Do you want me to show the outline?
Yes.
Yeah. The outline summary, today's lesson plan. I don't know how you're defining it.
Okay, the outline, yeah, at the beginning. Okay, can you so can I share the screen, Mr. Pham?
At a minute, I need to go.
Thank you.
Okay, so this is the.
There we go. Thank you.
Okay.
That's it.
And thank you, Mr. Pham, for your help this year. Just to let you know, since today's the last day, hope you're safe. Everybody's safe. Don't drink and drive. And See you next year. No need to drink and drive. There's plenty of time to call a friend or get on the bus, taxi, whatever. Just be safe.
Okay.
Thank you.
I get a question. You say on this display. So where basically what you think what I supposed to do.
Well, I missed this page initially when we first started the class. And I know you always have it displayed as your lesson for the day or your plan for the day or your summary, your outline. I mean, different teachers have a definition for this. They have a definition for this page. So that's all I was requesting.
Okay, so basically for the whole week, you want first day what we doing, right?
I just wanted to see this today's this page, today's
daily outline. Yes.
Yeah, today's daily outline. That's all, Mr. Pham. Thank you.
And I usually have them here. So if you ever need it, just let me know. And pretty much that this is on the 7th, and usually I take a screenshot, and which is I keep a track of something like this.
You do a full screenshot and have a link on the webpage then?
No, this one is just for my own personal, because I always keep track of what we covered, so that way I know as I can see whatever I go over and sort of make notes for myself, and what was the lesson plan, the outline for the lesson plan for the daily. Okay, so I consider do it like that, just kind of take a screenshot and then just paste on my notepad, my PowerPoint, so I know exactly what we're covering. And
yeah, that's what I usually do too. I start a PowerPoint, do my notes. So I just missed today's page. Thank you.
Right. Okay. So, all right.
Quick question.
Yeah.
Yes. Go ahead, Sophia.
Is the lab schedule the same as last week, except for it being tomorrow and Wednesday?
Exactly.
For the same people?
Exactly.
Okay, thank you. That's all I need to know.
Okay, sounds good.
Okay, so if no more question, okay, so I agree to say Merry Christmas and Happy New Year.
Thank you very much.
Merry Christmas,
Yeah,
Happy New Year.
Merry Christmas,
Holidays.
Bye.
Bye.
Good night.
Good.
Bye.
All right.
Bye.
Bye.